So we're going to look at a recap of polynomial division. You may remember it from, what year, 10? Was it only last year? Looked at polynomial division? Okay, so let's have a recap of how we do that. It's basically this idea that any time you want to break something down, you can write it as a divisor times a quotient plus a remainder. Now, the first time you saw this idea was before you knew about algebra. I remember doing long division back in primary school and things like that, and you'd do your long division and you'd have a remainder, what have you. It all comes from the same idea. And in fact, that is what we're doing in a polynomial division. We're doing long division. It's just with algebra instead of just whole numbers. A couple of minor things. You don't really need to worry about this because naturally you would keep going anyway. But the degree of the remainder will always be less than the degree of the divisor, because you keep dividing until the degree comes down. So once you look at your remainder, if say you're dividing by a quadratic and the remainder is a cubic, well, you can keep going because a quadratic will go into a cubic. But if the remainder was a linear function, you'd stop because you can't put the quadratic into the linear function. And again, very trivial, this one. Qx and Rx are unique, which just means they're different. Because, well, if they were the same, we'd be able to factorise it and we wouldn't actually have a remainder then. So let's look at an example, very old example. 1998 HSC. Saw this one, wow. Now, when we set up the division, you'll notice what I'm dividing into, I've added a couple of terms. So those missing terms, I write in 0x cubed and 0x. It's just so I've got the columns to line up with when I do the division. And when you are actually dividing, really you're only dividing the leading term by the leading term. So x to the power of 4 divided by x squared would be x squared. Then we multiply out and place the algebra in the appropriate column. So I've got x to the power of 4 plus x squared. And then we get our remainder. We subtract. The x to the 4 disappears, which we expect because we've just done the division. And in this case, I'm left with minus 2x squared, but I then bring down the other terms at the end. I can keep going because a quadratic will go into a quadratic. So minus 2x squared divided by x squared is minus 2. That gives me minus 2x squared minus 2. Do a subtraction, I'm left just with the constant number 3. That's going to be my remainder because I can't divide a quadratic into a constant term. So what we can do is we know, all right, so the quotient for this one is x squared minus 2 and the remainder is 3. 1988 then. Here's the division they had to do that particular year, so let's do it. Okay. 2x to the power of 4 divided by x squared gives me 2x squared. Multiply it out. Let's do a subtraction. I'm left with a cubic, so I can keep going. Divide, I get minus 4x. Subtract, quadratic. I can keep going. Minus 2. I'm left with negative 1. That's where I'll stop on this one. So hence go and write it that way. Gx, just to confuse everyone, because we always say ax, but they thought, no, we'll make it gx. So there we go. We can write it as divisor times quotient plus the remainder. We've talked about this idea when we're graphing as well, but where polynomial division really is useful is those sorts of graphs. In fact, in yesterday's 4-unit paper, wow, in yesterday's paper, there actually was a question based on this idea where they had a polynomial on a polynomial. You had to find the asymptote and then draw a picture. So how do we do it? Once we break it up using our polynomial division, remember the bottom of the fraction? Bottom of the fraction can't equal 0. That tells us where the vertical asymptotes are. The quotient turns out to be the horizontal or the oblique asymptote. And in fact, that was the first part of this question. It said to do the division, and then it said, oh, what would the oblique asymptote be? Now, the top is useful because sometimes you cross the asymptote. Can't cross a vertical one. You never cross a vertical one. But you can cross a horizontal or an oblique one. So you solve the top of the fraction to find out where, if it's going to happen. So let's draw this one. We'll do y equals x plus 8x on x squared minus 9. So I've already broken it up. Vertical asymptotes would be at plus or minus 3 for this one. So let's draw those in. Whee! There. Vertical asymptotes. The oblique asymptote then would simply be the line y equals x. So let's draw that in. There it is. Now, in this case, it will meet the horizontal, or sorry, the oblique asymptote, because it is possible for 8x to equal 0. So I know at x equals 0, it will cut it. Well, we knew that anyway, because we could have found our x-intercepts and known that. But it confirms that one. There's the actual graph then. Okay. Now, how do I know where it goes? Because if that's the only x-intercept on the whole graph, then on the left-hand side, it must be cut in this little triangle here. Because the curve always bends towards the asymptote. If it was in the other one, I'd need an x-intercept, and I haven't got one. So it must be down there. Similar for the right-hand side. Now, for the bit in the middle, how do I know it goes this way and not the opposite?
Oh, would it just be
Very good. Did everyone hear that? It had to go this way. Couldn't go the other way, because if it did, it would have to cut the oblique asymptote again. And we've found it's only got it once. So very good. Very good. 4C.